All right.
Hey everyone, how you doing? Rich Ozer here and Gerald McKeegan. And
Good evening.
we're at the Chabot Space and Science Center, and behind me is Nellie, our 36-inch reflecting telescope. So far, it's clear, so we will be able to do some live viewing, and humidity hasn't reached a point where we have to be concerned yet. Somebody did mention on the Facebook page that they're just a mile away and they're getting pretty fogged in already. So we'll just have to watch it carefully. We're going to start by getting a view of the comet because that's what everybody is talking about and photographing. And this is Comet NEOWISE. I'm sure you've seen photographs of it on Facebook and on the news. And it is just turned into an evening object, and let me get it worked out here. All right, share my screen. There we go. So there's Comet NEOWISE through the 36th inch. That is the head of the comet, the bright area. You'll notice that it's got kind of a greenish tinge. A lot of people have been, I think we got an echo. Sorry about that. We're still playing with microphones here. All right. Sure. All right. So a lot of people have mentioned that the color has changed to a green tinge in the last week or last few days. And it's very noticeable from here.
Yeah, that's typical of a lot of comets. There is an ice on the comets called cyanogen, and when it sublimates, when it switches from solid ice to a gas, it has that greenish tinge to it. So that's pretty common for comets.
So the comet, look at this yourself, then you want to be looking underneath the Big Dipper, and it's going to get a little bit higher each night, but right now it's pretty well positioned in the sky. So grab a pair of binoculars if you want, go outside and look just straight down below the Big Dipper, and you might be able to catch it.
Yeah, you definitely want to use a pair of binoculars. If you're in a really dark sky location and away from the fog, you might be able to see it naked eye, but it'll look like just this very, very faint smudge in the sky. But in binoculars, it pops out pretty easily. And of course, if you've got a camera and you want to go out and take some pictures of it, it looks great. There's been a lot of photographs. In fact, I brought a few along with me if you want to share them. People have taken photographs both earlier when it was a morning object and now as an evening object. So, by all means, try to do that. Some of you may have smartphones that have night view on your camera. And if you have that, then you want to switch to night view, and you should be able to capture it.
Gerald, somebody asked a question. They want to know how we know the orbital period of the comet.
Oh, great question, actually. The comet was discovered on March 27th by the NEOWISE spacecraft. NEOWISE is a spacecraft that is in a polar orbit around the Earth. It's actually what's called a sun-synchronous orbit. So it is always getting its batteries recharged by the sun. And it has an infrared camera on it. And NEOWISE was originally launched to do surveys of stars and galaxies and nebula and so on in the infrared spectrum. In 2011, it was repurposed to search for near-Earth objects using the camera, which can see near-Earth objects better because they are brighter in infrared than they are in visible light. So on March 27th, NEOWISE discovered this comet. It was still pretty far out, but it was headed inbound. And by taking multiple observations of the comet over a period of time by NEOWISE and by a number of ground-based observatories, we were able to calculate the orbit. This is actually a pretty common technique used to calculate the orbits of comets and asteroids. You just take multiple observations over a period of time. We use a technique to precisely plot the position of the object in each image, and then using that, we can calculate the orbit. This comet has an orbit that comes from the Oort cloud, which is way out at the farthest extreme of our solar system. It's more than 1,000 times the distance between the sun and the earth. So it's way out there. It's very cold out there. That's why everything is ice on these comets. In fact, I'm going to pull up an image here that I have, kind of give you an idea of what the orbit looks like. Let's see if I can share that. It doesn't look like it'll, oh yeah, well, okay, here we go. Yeah. Yes. Okay. All right, where is it? Oh, here it is. Okay, so you see the orbit. We're just seeing one small part of the orbit. The orbit is highly elliptical. It extends out to the Oort cloud. It comes in, goes around the sun, very close to the sun, and then it heads back out. It actually was closest to the sun, the point we call perihelion, on July 3rd. And it is now on its outbound leg. But as you can see from its position there, on its outbound leg, it actually gets a little closer to the Earth. And so it's actually getting closer to us right now, and it will continue getting closer to us until the night of July 22nd. And then it will start moving farther away from us. But you'll still be able to see it well into August with a pair of binoculars. Like I say, it came from the Oort cloud. Oort cloud is a swarm of icy bodies way out at the fringe of the solar system. And periodically what happens is one of those objects gets knocked out of its orbit, either because it collides with another Oort cloud object or because of a gravitational tug from a passing star. And then it makes its long journey towards the sun. This particular comet has an orbital period of roughly 6,800 to 7,000 years. We're not real precise about that. And one reason for that is that because it's outgassing, because you see all that material being blown off the comet, that actually affects its orbit. And so we can't use the same techniques that we would use for an asteroid, which is not outgassing material. We have to use a little bit of extra math in order to calculate the orbit. So its orbit is a little less than 7,000 years. So if you miss it now, you're going to have to wait nearly 7,000 years to see it again.
Well, the advantage is next time it comes around, we'll have much better cameras. And,
right.
And we'll be able to see more of the tail. So I'll get ready for that.
Okay.
Hold on, let me share the screen again for the, bear with me, folks. There we go.
Let's see, is that still a still shot?
Yeah, it's still shot. I'll take the
take
a fresh one here.
We probably have drifted.
Probably going to have moved.
Yeah, the comet is moving across the sky. It's moving.
Okay, that's pretty good. Yeah, you'll see that in the last 10 minutes of talking, it moved about, an inch across the screen to the left there. So that gives you kind of a sense on the direction and the rate.
Yeah, its motion is actually about 9 arc seconds per minute of time. So we measure distances across the sky using angles, so degrees, minutes, and seconds. 1 arc second is 1/60th of an arc minute, and an arc minute is 1/60th of a degree. So it's moving about 9 arc seconds every minute of time. So it will drift off to the left there, as you noticed. And looks like Richard is playing with his exposures here.
Yeah, I got a little bit more of the tail by stretching the image there a bit. And that's the ion tail. I mean, the
particle tail.
Particle tail. The ion tail would be, if we were able to see it, it would be coming off kind of like this, following my cursor. But I've not been able to get a view of that yet.
Yeah. The ion tail, in all of the pictures that I've seen, the ion tail has been very faint.
Yeah.
If you can just barely make it out in your image, it's going up and slightly to the left, or to the right rather, in your image. But it's pretty faint. So there are actually 2 tails to a comet, a particle tail and an ion tail or a gas tail. The ices on the comet, there are a number of different kinds of ices. There's water ice, carbon dioxide ice, cyanogen ice, methane ice, and so forth. And as it gets in close to the sun, that ice begins to change from the solid state to the gaseous state. And that's a process called sublimation. And as the ice sublimates, all of the dirt that's in the ice gets released. So there's sand and pebbles and small rocks within the ice, and that is released as the ice sublimates. And the pebbles, the particles we call them, form a long kind of arcing tail that's often white or greenish white in color. And then the gas is blown away from the comet, but it's blown away in a different direction. The gas is blown away from the comet nucleus by the solar wind. And the solar wind is always taking that gas in the opposite direction as the sun is with respect to the comet. The particle tail is always following the path of the comet in its orbit around the sun. So it's not unusual for those 2 tails to be separated by quite a bit. In fact, in the right configuration, they can actually be going in the opposite direction. So that white bright tail that you see, especially if you take a photograph with your camera, you'll see that bright tail. That's the particle tail. And if you look carefully, you don't see it very well here, but with a wider field of view, you would see that tail has a it fans out and it arcs a little bit rather than being straight back from the comet.
It's kind of funny, as we do this, I watch it on Facebook to make sure that what we're doing is actually making it all the way to Facebook. And the view on the Facebook screen actually does a pretty decent job of showing the tail. It's actually getting a much higher contrast than on our Zoom screen here. So that's actually not bad. You might have seen some pictures of the ion tail floating around, and people are able to capture that by taking many images and stacking them and then enhancing the blue part of the photograph to bring it out. And I have seen some really beautiful shots of the 2 tails together. We do have a question. Someone wanted to know how far below the Big Dipper the comet is. And basically, if you take your hand and extend it out like this and put it just below the bottom star of the Big Dipper, it's about where the comet is. And kind of as a rule of thumb. And if you stand there with binoculars, you'll see it. You don't need to know the precise point. What you need are the binoculars. It's kind of tough naked eye unless you've got young eyes. And I know that right now, I really can't see it naked eye, but through a pair of binoculars, it wouldn't be any problem.
Yeah, another trick is to take your hand, and if you can imagine where the horizon would be if there weren't any trees or mountains or buildings, and take your hand and spread it like this, and put your thumb, the tip of your thumb, right on the horizon line, and the tip of your little finger will be at about the right height above the horizon for where the comet is. It's about a third of the way between the horizon and the Big Dipper. Oh, really? Yeah.
I am able to see it naked eye from here, and I guess I have young eyes, right?
Yes.
I don't
Yeah.
think so.
Younger than mine, anyway.
Yeah, it really it's kind of like I needed to already know what it looked like and what to expect.
Yeah.
With binoculars, it should be no problem at all.
Yeah. Now, one of the things, the reason we don't see much of the tail in this image is the camera is mounted on the 36-inch telescope, which is a very powerful telescope in terms of light gathering, but it has a small field of view. So we're only seeing the nucleus of the comet, the head of the comet, if you will, and a small portion of the tail. The tail actually extends more than 1 million miles out from the nucleus. So, when you go out there with your digital SLR camera and take an image of it, you get a much better sense of how long that tail is relative to the nucleus of the comet.
Good question. Do comets typically expire?
Over time, yes. Because the comet is outgassing, the ices are sublimating and outgassing, it is slowly losing mass. It doesn't lose very much on just one swing around the sun, but each time it orbits and gets close to the sun, it loses more mass. And over many orbits, hundreds of orbits, it will eventually lose enough mass near the surface to where it slowly stops sublimating. And what happens is down deep inside the comet nucleus, which is about 3 miles, maybe a little less than 3 miles in diameter, down deep inside, there's still plenty of ice, but a lot of that dirt and sand and gravel and so on that's released doesn't leave the comet. It actually stays on the surface of the comet. And pretty soon the comet develops this veneer of dirt and gravel and boulders and rocks that completely cover the ice, so that over time it eventually stops producing a tail, stops the sublimation process or slows it way down. And when that happens, the comet actually has more of an asteroid-like appearance rather than looking like a comet. And there are several asteroids out there that are basically old, dead comets.
You may have already answered this earlier, but what was the speed of travel? Did you have an estimate on that?
I want to say around 30 some odd kilometers per second. Its motion across the sky is 9 arc seconds per minute, but that's just the what we call plane of sky motion in our images. The velocity of the comet as it goes around the sun is constantly varying, and I believe it's somewhere around 35 kilometers per second right now.
Someone wanted to know if they don't have binoculars, can they use their digital SLR? Yeah, what I would do is use the widest field you can get on that camera. So if you're using like the 80 to 200 millimeter, stock lens, put it on 80 millimeter, or if you have a 35 millimeter lens, just use that, or even wider if you own one, and aim it below the Big Dipper and put it on a tripod, take a 5 to 10 second shot, and I'll bet you see it in the result. That's about what you want to do. The ISO should be at like 1600. So ISO 1600, 5 to 10 seconds, wide field of view, aimed below the Big Dipper. And even if you don't see it naked eye, you'll probably end up seeing it in your photograph.
Yeah, yeah. And you start out with a wide field, and that gives you a sense of where the comet is. And then you can kind of zoom in and narrow your field of view once you know exactly where it is in the sky.
All right, what do you think? Want to
well,
move on to something else?
I heard a rumor that the space station is going to be flying.
Oh,
by.
that's true. Okay, what time is it right now?
It is.
I can't see any of the clocks, even though I got all these computers here.
It's 9:50 right now.
All right, so we can keep talking about comets or keep talking about other. You could show maybe some of those pictures you.
Yeah. Why don't I show
and
some
we can
pictures?
come back to it. The reason we're doing this is that supposedly at 10 after 10 or 11 after 10. The International Space Station is supposed to cross the comet right about at the head of the comet. So there is a possibility we might actually see that if I take a lot of photographs until it actually happens. So we might give that a shot. It's 50-50. So maybe Gerald, you can put on the other presentation, and
all right. Let me share my screen here. Here we go. So hopefully you can see that. This first image was taken by Bob Miner. Bob is a member of the East Bay Astronomical Society, and he took this about 2 weeks ago when the comet was a morning object. And you can see how long the tail is. That tail extends all the way up to the top of the frame. And you also can see that it is a curving tail. So that is definitely the particle tail that you're seeing there. And he took this from Tilden Park, up, I believe, at Inspiration Point. Let's see here. There we go. Okay, this second one, let's see if I can remember who that was taken by. Yeah, that was taken by Gert's wife. Gert Gottschalk is, bear with me just a second here. Gert Gottschalk is another member of the EAS, and Gert is German. His wife often spends time in Berlin. And so this is an image that she took with her smartphone. All right, let's see if I can get another one here. All right, this was taken by Wes Chang. Wes is another EAS member. I'm not sure what the lake is. If Wes is on, maybe he can put a comment on about what the lake is that we're looking at in the foreground. But you can see the comet in the background. And again, this is a morning shot that he took, a really great shot. All right. Oh, this is a good one. Alan Roche, another EAS member, was also up at Tilden Park, Inspiration Point, and he took in quite a few images of the comet, got some great shots of it. After he was done photographing it, someone asked him if he saw the International Space Station, and he said, "What?" And they said, "Well, the space station would have passed close by it." So Alan went back and started just thumbing through all of his images, and sure enough, he found one where he had the space station in the frame. So that long streak that you see, that is the International Space Station orbiting. It's physically not close to the comet. It's just from our line of sight, it looks close to the comet. This image, I believe, was about a 6 or 8 second exposure. And that's why the space station looks like a streak rather than a bright dot in the sky. All right. Here's an image taken by Dan Vanderzanden. Dan is one of the volunteers here at Chabot. He's also a member of the Foundation Board of Directors for the Chabot Space and Science Center. And again, you can see how the tail kind of fans out and curves a little bit up and to the right. And so that tells us it's the particle tail. All right. Dave Shaw is a EAS member, also one of our telescope operators here at Chabot. And he has a second home up near Lake Almanor, up in the Sierras. And they get nice dark skies up there. And so he was able to capture this image here a few days ago. And as an evening comet, the tail is not pointing straight up anymore. It's now pointing up and to the right, like you see here. And that's just because of the comet, as the Earth rotates, our angle of view changes. In fact, the way it works out, the comet is above the horizon just barely in the early morning. And as the Earth rotates, the comet actually rises and it's up high in the sky during the daytime. Now, obviously, since it's daylight, you can't see it. But then as the Earth continues to turn, the comet, just like the sun, moves towards the western horizon. And because it's a little bit behind the sun, it's still up after the sun has set. Excuse me. Got some dust in my throat. All right, one more, I think. Oh, yeah, this one I took from very light polluted skies in Walnut Creek. And there's a map of where to find it.
Oh, nice. That's a good map. I like that. So the Big Dipper is pretty much center of the screen there.
Right here, there's a
And
Big
then
Dipper.
if you follow, show the that angle on the two stars on the Big Dipper. There you go. Yeah. And then you could just go down.
Just come on down, and about a third of the way up between the horizon and the Big Dipper, that's where you'll find it. Okay.
Do we have a way to estimate the age of a comet?
I'm not sure. I think maybe by looking at its composition, we can get some idea of it. But generally, comets are extremely old. They are left over from the formation of the solar system. So they're typically 4.5 billion years old. Like I say, these originate out at the very fringe of the solar system. And when the solar system formed, all the gas and dust that swirled around the protostar, most of it formed asteroids and planets. But what was left over at the very fringe of that gas cloud became all these icy bodies, and they've been orbiting around the sun. And their orbits take hundreds of thousands of years, depending on how far away they are. The outer fringe of the Oort cloud is actually a little more than a light year away from the sun. So that gives you an idea how far away they are. And these objects have been sitting out there, slowly orbiting the sun. And every once in a while, something causes one of them to be dislodged from the Oort cloud, and they come in towards the sun, and we see them as a comet.
Okay, I'm more or less set up for this if we're going to be able to actually see it. It's like hitting we're basically looking at a bit of the sky about the size of a pea, and we're hoping that the International Space Station passes through it.
Yeah.
I don't know. I mean,
now
this
you
works.
said
I'm going to go out and buy lottery tickets tonight.
You said it was supposed to pass very close to the head.
Very close to the head, so we got a good chance of seeing
I
it.
wonder if we need to reposition the telescope a little bit.
Put the head further up in the.
Yeah. Are you in live view now?
No, I'm not. I can do that.
So we'll get it centered up in the field of view, and
I think that'll be good. Might as well have a nice view of the tail while we're doing it.
So that's
We'll
live view?
see. Okay, we could start a betting pool here. On,
Is that live view, Richard?
no, it's not live
Yeah.
view. I'm just taking frequent short exposures.
Oh, because the space station is going to go through the frame real fast. So we
It's
want
going
to
to
be.
be, I'm going to start taking photos one after another. They're 2 seconds long. And we'll see if we can catch it. And that's going to be at 10, 11, and 58 seconds, apparently. So we've still got 10 minutes.
So for those of you who are living down in, Oakland or Berkeley, you probably are looking up and seeing fog and wondering how we're doing this. We're kind of fortunate. The fog is below us right now. So we are fog free up here at Chabot. And so we've got great views of the comet. And after we're done looking at the comet, we'll have a chance to look at a few other cool objects. And then a little later on, we'll actually be able to see Jupiter and Saturn. So lots of things to look at tonight. But right now, our focus is on the comet. Now you see a few other dots in the frame there. Those are actually background stars. And as the comet moves, it will change its position relative to those stars. There was a question a while ago about how we are able to track these and calculate the orbits. Actually, one of the things we do is we take images like this and we identify stars in the image. And we then develop an equation that relates pixel position of the image to the star's coordinates in our astronomical coordinate system. And once we do that, we then look at the pixel position of the comet, and we can convert that to what we call right ascension and declination, which is our coordinate system that astronomers use for objects in the sky. And once we have that information, we can then go ahead and calculate the orbit. But we can't do it based on one observation. Despite what I've seen on a few dramatic TV shows about comets and asteroids, it takes more than one observation in order to calculate the orbit. Typically, it takes 3 or more observations over a period of time. And the longer the observation arc, in other words, the longer the period of time between each image, the more accurate is your orbit calculation. And the calculation process itself is actually pretty complicated. The original technique was developed by Carl Gauss back in 1801. And he did this after the first asteroid was discovered. Ceres was discovered by a guy named Piazzi, an Italian astronomer. And he was only able to observe it for a few weeks before it got so far over into the twilight sky that it was no longer observable. So all the astronomers of the day wanted to figure out when would they be able to see it again, and nobody knew how to calculate that. So Carl Gauss, who was a brilliant mathematician, he figured out a way of doing it, but it was a really complicated process of multiple calculations in order to develop a prediction for where the comet or the asteroid would be a year later. And it turned out that it worked pretty well. And based on his prediction, almost a year after the original observation, it was observed again right where Carl Gauss had predicted it. So it was pretty cool. And today, like I say, it was a very complicated set of calculations. There's more than 80 separate calculations that you have to do in order to determine the orbit of an asteroid or a comet. And back then they did that all by hand. Today it's all done by computer. Once we have the coordinates of those individual frames, we can plug those coordinates into the computer software and it will pop out an orbit prediction literally within a fraction of a second. So, one of the great advantages of computers is how fast they can do calculations that used to take hours. I notice you're setting up something there, Richard. What you up to?
Well, I figured I should take. Sorry, I figured I should try to take a whole sequence of them automatically, but I'm trying to decide whether I just want to keep hitting the button manually or have the computer take a whole series. I haven't decided yet. I got 5 minutes to decide.
Yeah, we are approaching our limit though for hopefully it'll be we'll see the space station before we reach the limit.
Yeah.
As we're at a zenith distance, actually we're over it. So in about 2 or 3 minutes here, the software is going to stop the telescope from tracking it. So
yeah, so this may be
it's going to be tricky.
Fool's errand in a couple more minutes.
Yeah. So let's see. You said 10:11 is when
10:11 and 58 seconds. So essentially 10:12.
Oh, okay. Well, keep your fingers crossed here.
Yeah.
Because we're getting really low. And this is live view?
No.
Oh, okay. I see the live view button up there.
Yeah, just the button is just there to tempt you.
Yeah, I've got the telescope slowly adjusting periodically in the direction of the motion, so that helps keep it centered in the frame pretty well. So let's see if I got any other images I can show you while we're waiting here.
Well, it's 10:08. So maybe we should not upset the Zoom gods.
Yeah. Are you just?
I'm just manually doing it because I want to see the photo. When you do the sequence, it doesn't always refresh the screen as quickly as it's taking photographs. But if I do it manually and actually let the screen refresh, there's a better chance we'll actually see it if it does pass through the field of view. So I want to obviously show it to everybody and not search through a stack of photos.
Okay.
Oh, that was good. Yeah. I see what you did. I see what you did there.
Yeah, I'm gonna adjust it a little bit more here. Get it closer to the middle of the frame. There you go.
All right, it's 10:09. Just a few more minutes. Oh, somebody said they got a picture. Cool. One of our viewers here went outside and got a picture. Why are comets so bright? Well, they're bright because they're reflecting light off of the sun.
Yeah. Now
and they become very, very dim as they move farther away from the sun until they're absolutely invisible. Yeah, we're really tempting fate here. We got It's 10:09. We've just got a couple more minutes. All right, 10:10. And one of our club members told us about this passing of the space station in front of the comet. So hopefully he got that time right. All right, it's 10:11 now. So I'm just going to keep shooting. We'll see if anything shows up. Yeah, that would be helpful. Yeah. Gerald's going to climb on a ladder. Let's see if he can see the ISS.
Yeah, see the space station now? And it should be going by it here in just a second, if it's going to pass. All right, should have passed it by now. Okay, we missed it.
All right, no lottery tickets for me. Well, it was a good try. All right, well, we didn't crash the telescope into the floor or anything, so
Not yet.
So I think that's it for the comet for tonight.
Yeah, we're going to have to move the telescope now to a different object, and probably going to
All right.
to manually move it because it's below the limit. So
All right, well, take your time.
Here we go.
Maybe we could take a look at the Lagoon Nebula next if you want. We also have planet opportunities.
All right. All right, I'm going to pick a bright star and hopefully we're going to find it. Oh, look at that.
Yep. Pretty good. Pretty close. I'll get it right center.
I got it. Yeah. Yep. All right. Okay, we didn't screw up the telescope. That's good news. Okay, so where should we go from here?
Want to take a look at M8?
At M8?
Yeah.
Okay, hang on a second. Let me get a telescope in a more normal position here.
Mind if I do a quick focus?
Yeah, can you reach it?
I think so. Let me give it a shot.
Yeah, wrong way. There you go. Oop. Right about there.
Yeah, it's better. Okay.
Okay, I'm going to move it a little farther here and get it. It's still pretty far over. Oh, look at that. Double star.
Oh, yeah. I know that double star.
Let's see, M8. Where is M8?
M8 is in the southern Milky Way, so it's going to be in.
Okay, so we need to go pretty far
Paris.
south, huh?
Yeah, yeah.
All right. All right. Well, let's head to Arcturus then, get the telescope working its way south.
Good.
All right.
Arcturus.
Yep. All right, big move now.
You're going to stop at another star? Like
Yeah, one more and then we'll go to M8.
Okay. All right.
All right. Is that it? Boy, we really missed it.
Well, at least it's in the field of view. It could be worse.
Yeah, one of the things I slewed quite a bit to the east, and one of the things that we've noticed is that it lags a little bit when you slew to the east. That's why we do this. Okay. So M8.
All right, I'm going to take it out of live view
Here we go.
and set it up.
Looks like a comet. Oh.
Yeah. Yeah, that's the thing. We always confuse people because when I'm ready to actually shoot, it shows the last picture that we took. So I'm going to take a 20-second shot here and see if we see anything.
All right.
Yeah, we do. So let me adjust the. All right, there we go. I'm going to take a little bit longer shot, and then we'll talk about what this is in a sec. All right, I'll take that. Shoot. I'm going to get an extra 10 seconds in here.
Okay.
Make it a 30-second shot. Bring out a little bit of detail. We showed some photographs of this a few weeks ago when we were clouded out, and we were talking about star forming regions and how there are different types of nebula. Some nebula are from regions that are forming new stars, and others are left over from stars that have exhausted their fuel and have essentially died. This is a star forming region, and let me adjust the contrast here a little bit. I can see it. Yeah. Okay, so it's called the Lagoon Nebula, and it's called the Lagoon Nebula because of this kind of wide area down here. Kind of looks like a lagoon. And you know, you got to use your imagination for some of this stuff. This is an interesting object in that it's one of the two nebula in the sky that are considered naked eye. Now, I can't imagine seeing this naked eye, but in a
especially around here.
Sky, yeah, in a very, very dark sky, supposedly this is a naked eye object. I can't say I've ever experienced that, but some people have much better eyes than I do. Most people have much better eyes than I do. So it's called M8 because it's named after Charles Messier, who is the M stands for Charles Messier. And he lived in the 1700s, was a French astronomer, and put together the first catalog of deep sky objects and interesting star formations as well. It was discovered, though, almost 100 years earlier by another astronomer, but had not been cataloged until Messier came around. But there are notes from this other astronomer, and I can get you his name, actually. Somebody I hadn't even heard of. Let's see if I can pronounce his name properly. It is Giovanni Odierna. So that sounds like an Italian astronomer. And that was sometime around the 1650s. And then 100 years later, Charles Messier added it to his catalog. So anyway, that's the Lagoon Nebula.
All right. Yeah, this is in a region of the sky that's actually pretty tough for us to look at from here at the Chabot Observatory. This is almost straight south from us, and it's very low in the sky. And as it turns out, when we're looking in that direction, we are seeing a huge amount of light pollution from Hayward and San Jose, that whole area down directly south of us. Light pollution and air pollution really distorts the image that we see. And so, as Richard was saying, you get in a dark location somewhere high up in the mountains where you don't have all that light pollution. This looks a lot better.
The other thing we can do, if you want, people were pretty excited to see Jupiter last time, and we've got a pretty clear view at this point, it looks like. What do you think?
Yeah, we do. We do. Yep.
Let's do it.
Yep. We can go.
Let's do planets again. That was fun. I even figured out the right exposure. Let's see if I can remember it.
All right. So we're going to go to Jupiter.
I'm going to put it back on live view.
All right. And away we go.
Yeah, there it is.
There it is.
There's
a moon.
Centered. Let's get it centered, then I'll adjust the exposure.
Whoop, wrong direction. Oh, got 3 moons.
All right. All right. Take it out of live view. And I'm going to shoot.
It suddenly looks like a
400. And it's going to be. Oops.
While you're doing that, I'm going to open.
40th of a second. Right.
I'm going to open up Stellarium and see if I can figure out which moons are which. Maybe.
There we go. So you can see the cloud bands in the image. You'll notice that there's a band. You can see one of the two more prominent ones, and then this is the southern and this is the northern here. It's upside down. And I don't believe we have a view of the red spot tonight. No.
No, we don't.
Yeah.
No.
That's a kind of a treat we got last time for those who didn't see it. And what I got to do is I'll take a series here and stop on the ones that look sharper than the others.
Yeah.
We're fighting what's called the atmospheric seeing, and we have to wait for a moment. Yeah, that one's pretty decent. we have to wait for kind of a moment of clarity, and we luck out if we take a shot when the atmosphere is steady for just that one moment.
Now, if you expose longer, you would see the moons. There's actually a couple of them.
I could do that so you can see the moons. Hold on for a moment. Let me just do temporarily a more sensitive exposure. There you go. So these are, which two moons are that, Gerald?
The two on the left are Io and Europa.
Okay, and we don't see the one on the right. It's off.
Yeah, that's Ganymede on the right.
Io, I presume, is the closer one here, unless I've got the orbit wrong.
Actually, no.
Is it the other way around?
Europa is the closer in this view, and that's just because of the orientation.
Yeah, it's because of the orientation. You could think of Europa as being in the background. It's coming around, and it's going to overtake Io and be out here sometime, in the next several hours. All right, I'm going to put it back at ISO 200 so we can see some detail on Jupiter. There we go. Just keep taking them until you get a good one. That one's okay. There.
Looks like you maybe need to
the seeing
stop it down a little bit more.
Yeah, the seeing is not very good tonight. But
yeah, we've got a little bit of wind up here tonight. The humidity is low, but we've got some wind, and wind creates turbulence in the atmosphere.
Yeah, that one's decent.
Atmospheric turbulence distorts our view. It scatters the light from the planet more, and that makes it a fuzzier view and makes it harder to see fine details. There you go.
That one's decent.
Yeah, that's a good one.
All right, we'll stop there for a minute.
So you see the equatorial belts, those dark bands that you see. One's just above the equator, and the other is just below the equator. The southern belt actually is where the red spot would be. However, the red spot is not visible right now. Jupiter takes about 9 hours and 50 minutes to make one rotation on its axis. And just to compare that, it takes the Earth nearly 24 hours to make one rotation on its axis. Jupiter is 11.2 times the diameter of the Earth, so it's way bigger than the Earth. So you want to think about that. It's rotating much faster, more than twice as fast in terms of the angular rotation rate, and yet it's this huge planet. And that means that the clouds in the atmosphere are swirling around the planet at a very high velocity, well over 1,000 miles an hour at the equator. And there are high and low pressure areas in the atmosphere, and they get wrapped around the planet. So when we see those dark bands, that's typically a low pressure area, and the lighter bands are high pressure areas. Now, if we could zoom in, we would see a lot more detail. We would see all kinds of swirls and eddies
and
festoons and what is it? Barges? That good stuff.
Barges and festoons. Those are great words. The festoons are actually interesting. I built many years ago, I built a 10-inch reflector telescope, and interestingly enough, the only time I ever really clearly saw the festoons on Jupiter was before I put the reflective coating on the mirror. And I had installed the mirror to test the telescope and to make sure I had everything lined up properly so it would focus properly. And I got this amazing view of Jupiter's festoons. They're actually they're kind of perpendicular to these cloud belts. They kind of branch off like curves off of the cloud bands, and they're kind of a greenish color, and they're quite amazing looking. But that's really the only time I ever saw them really well in a smaller telescope. I have seen them in some larger instruments, and obviously some photographs. I've seen them. But that's a hard one to catch. You got to have really good seeing, and got to have just the right telescope at the right time. Seeing if there's any questions here. What is the gravity like on Jupiter relative to Earth? That's a cool question.
Well, it's kind of hard to describe because on Earth we feel gravity because we have a solid ground underneath us. But Jupiter is a gas giant, so it doesn't have a solid surface the way the Earth does.
Well, let's say it did.
It would be several times our normal weight, normal gravity. I don't know the exact number off the top of my head, but Jupiter has a lot more mass. I could probably look it up if you want to stand by for a couple minutes here and tell you what it is.
We're in no hurry.
All right.
Yeah, it would be a very uncomfortable place to be.
Yes.
There very well might be a solid rocky core. It's all speculation. It may be molten. Nobody really knows. But it's mostly gas. So you would just fall a long way. But if there was a surface, then you would feel the full pull of Jupiter's immense gravity.
Okay, well, actually, it's not as bad as I thought. The gravitational pull of Jupiter at the 1 bar level, so that's the level at which the atmospheric pressure is the same as it is on Earth. The gravitational pull at that level, which would be actually fairly high up in the atmosphere, is 24.8 meters per second squared compared to 9.8 meters per second squared on.
So it's about 3 times.
Yeah, two and a half times. Yeah.
Okay. 2.5 to 3 times.
Yeah.
All right. Well, that sounds very uncomfortable to me.
Yeah. Now that's assuming you had a very tall platform mounted so that you could stand at the 1 bar level, the one atmosphere level, which is, like I say, that's not too deep into the clouds, because the pressure goes up quite a bit as you go deeper into the clouds.
Someone asked the question. They wanted to know if we had already looked at the comet. They joined late. Yeah, and the nice thing about this format is if you go to the Chabot page on Facebook and click on the link that says videos, you'll see all of these events going back many, many weeks. And you could just rewind to the point in time that we were showing the comet, which is pretty much starting at the very beginning of tonight's presentation. So yeah, you could always come back later and watch the part you missed.
Yeah, unfortunately, the comet is too low now.
Yeah, we can't look at it now. I guess we would crash the telescope, and it probably wouldn't even see it. It's probably below the wall now. The other thing that I wanted to mention is that if you enjoy these programs and you want to help us out, there is a donate button on the Chabot Facebook page, and as well as on the main website, which is chabotspace.org. And we can really use your support now. We are closed as a public center right now, and our revenue really depends on donations, as opposed to the past where we had events and paid events going on at the center. So if you can, give it a thought and send us a donation. What you looking at? Looking for Saturn?
3 or 4 minutes, and we should be able to see Saturn.
All right, we'll go to Saturn next. Take a couple more shots of Jupiter, see if we get another, if we luck out with a clear one. All right. It's worse.
Yeah.
Worse. One's okay. Yeah, this is the challenge this year. The planets are
Low.
low, so all of our photography for planets suffers up here in the northern hemisphere. If I was to go to south 1,000 miles, I might have an easier time of it.
Well, I do have a Nellie image that was taken a couple of years ago, if you want to look at that.
Yeah, we can do that.
Yeah, so this is an image that was taken under very nice conditions.
Yeah, I've seen amazing planetary views here when the sky is really steady and the planets are well positioned.
Right, there it is.
So, oh, that's amazing.
Yeah, yeah.
Who took that?
Conrad did.
Conrad took it. All right.
Conrad Jung is our staff astronomer here. He is an excellent astrophotographer. In fact, some of his work has been exhibited at the Smithsonian Institution. So that gives you an idea how good he is. Unfortunately, Conrad is currently being hospitalized, not because of COVID, but he did suffer a stroke a few months ago. So we are hoping for him to get back in the game again here real soon. But this is one of his many images that he has taken using Nellie, our 36-inch telescope. And you can see some of those festoons.
Somebody asked the question, what's the origin of Jupiter's moons? And really, we could say the same question for Saturn and Uranus. Most likely captured from the outer solar system, and it's a little bit less controversial than the origins of our own moon, which there's all kinds of theories, but that's the most likely answer, is that it's captured bodies. Although
some of it, the moons may have actually formed from the same
rubble, from like the rings,
from material that was forming the planet itself when it was first forming. I believe the count now is up to 82 moons around Jupiter. It's hard to keep track anymore.
Yeah, they're very prolific. Yeah, well, Saturn, most certainly there's an opportunity for lots of material to come together. Jupiter is a giant sweeper of the outer solar system, and it's very possible. I've heard some interesting discussion that life on Earth would not have necessarily occurred if it wasn't for Jupiter cleaning up all of the inbound bodies that would otherwise have made it to Earth's orbit into the inner solar system if it wasn't for the presence of a large, massive planet further out.
Right.
So it may have contributed to our very existence.
Yeah, one of the interesting things about Jupiter, we were talking about its gravitational pull a while ago. Jupiter's gravity is so strong that you're all being pulled by Jupiter right now. If we got rid of the Earth and got rid of the sun, you would fall onto Jupiter from this far away.
Is that why I feel light on my feet tonight? Okay.
So you want to go to Saturn?
Yeah, please. Let's do that.
All right. I think we killed enough time here.
Yep. Let me share the screen. Quick live view. Back to live view.
Yeah, Saturn's going to be a little fainter.
Yeah, well, that's fine. That will help. There we go. Okay.
Yeah, there's a planet with a ring around it.
This is live. I'm going to see if I can lower the ISO and just look at it live. Now, this is really, this really gives you an idea of what we deal with atmospheric seeing. And you could see how Saturn is kind of moving around. You see it kind of, weaving almost. And it's like you're looking at it while you're underwater. And that is what we mean by poor seeing. And when the weather is just right and the winds are very gentle and blowing steadily in one direction, and the upper atmosphere is not layered with radically different temperatures, but more gradual cooling as you reach higher elevations, then suddenly everything sharpens up, and you get these beautiful views of the planet with really sharp features. But that's not tonight, and that's one of the reasons why when we're, no matter what kind of telescope we have or what kind of camera we have, we often are stuck with blurry images, and we have to kind of wait for that special night when everything is just right. And when you have a really large telescope like Nellie, which is 36 inches in diameter, it's even more sensitive to those variations in the atmosphere. And sometimes a small telescope will outperform a large telescope with respect to clarity and just general ability to see detail on the planet.
Now I've got another another one taken by Conrad of Saturn under steady sky conditions. So if you bear with me here, I'll share my screen and show you that, give you an idea of what it looks like when things are really good. All right, let's see here.
Yeah, that's pretty good.
So you're seeing that?
Yeah.
Yeah. Okay.
That looks great.
Yeah. So this is under much better conditions. All right. Well, what else we want to do?
Well, maybe that's it for tonight. What do you think?
Well, one of the things we talked about earlier, maybe we can share it now. We tried once a couple of weeks ago to take a picture of M16, which is the Eagle Nebula. It's a huge cloud forming region. And I wanted to do a little comparison here. I'm going to show you a picture taken by Conrad Jung using Nellie, and then we'll show the same object photographed by the Hubble Space Telescope. And let me hang with me here for just a second. All right. Takes a few buttons to push here to share these images. Okay, so this is the image that Conrad Jung took of the Eagle Nebula. And this is a fairly long exposure, and it's processed a little bit, and it's natural color. So the colors you see are the natural colors. Mostly this is a huge cloud of hydrogen with a little bit of other elements, but primarily it's hydrogen and a lot of dust. And so you see the red color, but you can see those, what we call the pillars of creation. They're actually clouds where ultraviolet radiation from the very bright star right up at the top of the frame is actually pushing the cloud away from it. And as it does so, because there are smaller, younger stars embedded within the cloud, they tend to hang on to that gas, and you get that finger of cloud appearance. So this is taken in natural color by our telescope here. And what I want to do is see if I can stop the share for a second, and then I'm going to.
You're going to hack your way into the Hubble telescope?
Hack into the Hubble telescope, right. Right. Now, what's going on here?
There you go.
Okay, can you see that?
Not quite yet. Go ahead and hit that share button.
Okay. All right. Okay, there it is. So this is the Hubble Space Telescope image, obviously much higher resolution, but notice the different color. That is not the natural color. The image you saw before that Conrad had taken is in natural color. This is using what they call the Hubble Palette. And what they do is they assign colors to different parts of the image based on the precise wavelength of those parts of the image. So the part of the image of Conrad's image that was kind of orangish red, they have actually given it a different color. They've given it kind of that turquoise color. And what that does is really bring out the details and get you a lot more contrast, so you can see the fine details in this object. But this is a false color image, whereas Conrad's image was a real color image. All right.
Harold, what's somebody asked a question? What's Nellie's focal length?
Its focal length is about 7.5 meters or 24 feet. And that's the way we're using it right now. When we do asteroid work, we put a device on there that shortens the focal length to, instead of a f8, it becomes an f4.5. So it's roughly a little more than, or a little less than half the focal length. But right now we're doing it at f8, and the focal length is about 7.5 meters or 28 feet, or 24 feet rather. I'm sorry.
All right. Somebody wanted to know, do we ever look at constellations? Well, constellations are very large in the sky. They're, you know, if you hold up your hand in front of your face, that may be just a small part of one constellation. And our telescope is really looking at a very small part of the sky, like maybe a pea or a penny.
Yeah.
And no constellations fall within that that small an area. So we generally don't look at constellations with the telescope. We may point out constellations with a laser pointer or show people with a flashlight where in the sky they are. They're really just collections of stars in a particular shape named after various mythologies, or in the southern hemisphere, they're named after scientific instruments. But you can see a lot of constellations just from your front yard. Best way to do it is get a hold of a simple beginner's star chart. Go to skyandtelescope.com, anything like that, and you'll be able to print out maps of common constellations and find them on your own.
Yeah, one of the things I like to tell people is, if you can imagine taking a soda straw, holding it at arm's length and looking through it, that's about the field of view of this telescope in its normal configuration. So a very small portion of the sky.
Yeah, we'd be able to see the constellations if we were at another galaxy. Then,
yeah, there you go.
Then we'd be
There
able
you
to
go.
see the constellations in the Milky Way.
Well, I think it's time to start winding it up.
Yeah, I think so.
I want to make sure everybody is aware of some upcoming events. Next Friday at 8 o'clock, Chabot will be doing a Mars Madness presentation. Lots of different things about Mars. This is in celebration of the upcoming Mars 2020 mission that will send the rover to Mars. Rover and a helicopter to Mars. So that's this Friday at 8 o'clock. Also on the morning of July 30th, starting at 4 o'clock in the morning, we will be doing a launch party for the launch of that mission. The launch is actually scheduled for 4:50 in the morning, that specific time. And we will start our launch party at about 4 o'clock in the morning. So you can join us if you're willing to either stay up late or get up early, and we'll watch the launch and do some commentary about it and so forth. And that's about it. And don't forget to donate we could always use a little extra support here. All right. You're muted. You're muted. You're Richard just said good night, everybody.
I'm muted. Yeah. Good night, everybody. Enjoy the rest of your weekend, and we will see you next week.
See you later.